Okay, and we're live. We are live into another video. Welcome, everyone, back to yet another live stream. And you guessed it, we're doing Calc 2. We're doing Calc 2, everyone. Anyways, um, what is there to say? I don't know if there's a lot to say. I just went swimming, so I think we will succeed in whatever we're gonna do. And what we're gonna do today is an integration review for a test that we have on Thursday. On Thursday, I have module one test, which will cover all the techniques of integration that we learned. So that'll be just the basics of integration, and then we have our techniques, the substitution rule, like U substitution, integration by parts, trigonomic integrals and substitution, partial fractions, approximate integrals, and improper integrals. Now, am I ready for the test right now? Like, if hypothetically, if I were to take the test right now, could I do well? I don't know about that. I'm not sure. I think I could do fairly well, but I don't know if I would do very well. The U substitution rule, I think I have it, let's say 80% of the way there. I know that I have not mastered edge cases well, but I have mastered the general concept well, and I know that I can apply it to many problems. I know that. For integration by parts, I haven't had a lot of practice with it, but I know that when I did the homework, I understood it and mastered it very well. For trigonomic integrals and substitution, I think this is by far the hardest one. Although I have had the most practice. I think I did 3 days of like many hours with this topic. It was very tough, very tough. But we did it. We did it with this. What else? Yes. So what do I need to practice with this? I mean, I think I understand the concepts, but I like barely know them. I I have like just scratched the surface. I just need more and more repetition with them. For partial fractions, I think I know the general concept, but I still think I mean, I'm not prepared for any edge case problem, so that for sure is one to practice. So especially trigonomic, trigonometric integrals and substitution and partial fractions. Approximate integration, I think I've mastered it pretty well. There are some concepts that I wish to understand, but I think I understood that one pretty well. And for improper integrals, I think that was by far the easiest one. But of course, we can't. We should practice in this one. Let's see. What else? What else is there to say? No, I think that's it. And you're probably wondering, what are we going to do to a review? So what we're going to do is we're going to read a PDF that I already read, but I think I'll read it again in order to improve my cognitive retention of all these concepts. Then after that, we will do some exercises that we have in Infinity. Oh, grades. What happened here? Oh, very cool. Uh-huh. Yes, we will do some problems. I think these are all optional, but we can do them if we wish, and we for sure will do them because we want to master these concepts super well. And here we have some PDFs. In fact, here I will share my screen, but I think I'll stop sharing my screen for a big portion of the video because a lot of these tests, well, I can't share my screen because I think that'll be considered plagiarizing or not. I think like a violation of academic integrity, and that's what it will be. So as you can see here, we have our Calc 2 review for 5.5. That's for U substitution. So we should do these problems very well, and I think that the problem mentioned that I should do these without notes, so that's something to work on. Then we have 6.1. This is integration by parts. We have 5 problems to do, so this is important. We'll make sure to do those too. Here we have 6 problems to do for trigonometric in integration and substitution. So we'll make sure to do those ones. Actually, these are very good problems to do. Let's see. Then we have 6.3 partial fractions. We have 4 problems. So that's something to do for sure. 6.5, we have approximate integration. We also have 4 problems. Very cool. And then we finally have improper integrals. We have 12 problems. But of course, they're easy, so we're going to fly by these problems very easily. So I'm debating myself whether I should do these problems or um, whether I should do the actual homework pieces that are optional. What I think I will do for today, because we have these 3 things: optional, calc review, and this is not for credit, not for credit. Wait, hold on. If I go to grades, yeah, this is 0 out of 0, 0 out of 0, 0 out of 0. If I get 1, 1, 1, which we can, yeah, our grade will slightly increase. Oh, it won't change at all. Gotcha. Okay, anyways. So we have our questions here. I understand. Okay. In fact, I think I want to do this one again. Just real quickly. It shouldn't take long. It shouldn't take long. Oh, can we do this one again? Oh, it looks like we can't do it again. Anyways, in fact, it's fine. I I don't think I want to do it again. Now that I think about it, let's see. So we have these 3 things. Which one should I do? These or these questions? What I will do are these questions. We will do this later. So we should begin right now, right? Yeah, no reason to not begin. So here we go. Let's begin with reading our test review. Math 266, test 1, review. Integration with substitution. The idea is to recognize when an integral problem has the form of a function that came from applying the chain rule to the original function. To do these first, to do these problems, first find the inside function part of your integrand, which is a composite function, and let u be equal to that. Then compute the differential du. Substituting u and du into the original integrand should give you a new integral with only u in it. Triple exclamation mark. Find the antiderivative in terms of u first. Then put back your original variables according to your substitution. Yeah, so we solve the integral and then we replace u. Also, understand how to find the new endpoint for a definite integral question without going back to the original variable. Yeah, when x equals blah, what does u equal? And that's how we will change our lower and upper bounds for a definite integral. Easy. We all understand that. That's very easy. 6.1, integration by parts. Always choose u dv. I think, yeah, it says v dv, and I think it should be u dv. Always choose u dv such that it is easy to find its antiderivative. And if you have a choice, choose u such that its derivative simplifies the integration on the right-hand side. Remember the examples when integration by parts is used twice. Be able to find an integral using the boomerang method. I don't think I've heard of that. What is the boomerang method? Wait. Oops, bro. Boomerang method. Boomerang. Is there like uh integration? No, it's okay. Where are we? All right, it's fine. It's fine. It's fine. 6.1. If you have an odd power of sine or cosine, so let's do it this way. If you have an odd power of sine of x, rewrite the term as sine of x times an even power of sine of x. Right. If you have sine of x to the power of 3, an odd power, rewrite it as sine of x to the power of 1, or sine of x, times an even power, sine of x to the power of 2. And then use trig. Now, what does that do? We can use the identity sine squared, which we have from splitting the sine to the power of 3, equals 1 minus cosine squared of x. Right. And then we use the u substitution, cosine. What this will do is get negative the integral of u 1 minus u squared. Okay, I think some no. Sorry, we'll only get 1 minus u squared because du will take the sign. Right, and then in the other case, we have if you have an odd power of cosine, rewrite the term as sine of x times an even power of cosine of x. So we have cosine of x to the power of 3. And we get cosine times cosine squared. Then we use cosine squared equals 1 minus sine squared of x. Or 1 plus? Yeah, no, sorry, 1 minus sine squared of x. U substitution, u equals sine of x, and then we get a similar result. Very good. Otherwise, Otherwise, use double angle formulas in your integral. Okay, it's fine. Similar techniques work for the functions tangent of x and secant of x. Part 2. Understand the basic ideas of trigonometric substitution. Know when to choose and which function. Know when to choose and which function. We have our table right here and we should memorize it. Don't forget to restrict the domain to be able to work with the inverse functions. Right. From negative pi over 2 to pi over 2. Always draw a nice picture of a right triangle to express the trigonometric function needed in your solution. Yes. Partial fractions. Always divide first the numerator by the denominator using long division if the degree of the numerator is not smaller than the degree of the denominator. Remember the special cases, multiple factors and irreducible quadratic factors. Use the zeros of the denominator to solve for the constants in your form. If you have multiple factors or irreducible quadratic factors, then you have to choose some nice values and be able to complete the square technique in breaking up the integral into two pieces for the integrals when it consists of a single term with an irreducible quadratic as the denominator. So I think I've mastered this 60% of the way there. Partial fractions is what I need to work on the most. Know how to use a table of integrals. Know how to use a table of integrals. Always identify the constants you are using in your problem. Remember that for the reduction formulas, sometimes you have to apply the same formula again and again to obtain the final result. What? In some examples, you will have to transform the integrand into the form as in the table. This might involve a substitution or variables or completing the square. This is not approximation. Oh, this is approximate integration. I don't think we saw this. We did not see that. hold on. So okay. Right. All right, awesome. Cool. So now we begin to our review. So we should begin with this one. Hold on, I just need to wipe this. Okay, cool. Boy, I have like this nail over here. It's not cool. Okay. Here we begin. Matt 266, review section 5.5. Use sub. Can I zoom in? A weather balloon is being filled at a rate of R of t. So let's write that down. We have R of t equals 18 times 1 plus 2t, all of that squared. A weather balloon is being filled at a rate of R of t equals 18 times 1 plus 2t squared liters per second. So R of t second, starting with a volume of 0 liters at time t equals 0. So R of t is a rate of change. What is the volume of the balloon after 1 minute? The volume. Perfect. So classic example of integration. So we will say that V of t equals R, nope, sorry. V of t, in fact, we will do R of t equals V prime of t, the volume, the derivative of volume. So all we got to do to get V of t, integrate R of t. The integral of R of t equals the integral of 18 times 1 plus 2t, all that squared. So what is the volume of the balloon after 1 minute? So we're being asked V of 1. Perfect. So how do we do this? We have an inner function, 1 plus 2t. So we will let u be 1 plus 2t. du is therefore 2. Replacing, we get the integral of 9 times u squared du. And by the way, this is dt. Gasper, ow. All right, anyways. Wait, if du equals, okay, wait, hold on. That's so easy. Why am I hesitating? Wait, pause. So du equals 2, bro. Du equals 2. We have 18. Replace that. We 18. Oh, 2 dt. There you go. Oh, that's what I missed. There you go. We have 2 dt. Perfect. That's what we were missing. All right, u to 3. And we get squared. Whoops. Cubed. Perfect. My answer is 3 times 1 plus 2t to the power of 3. Perfect. We will come back to that. We will complete all these questions, and then we will check to see if our answer is right. Let's continue. So, all right. A balloon is being filled at a rate of R of t liters per second. Wait, sorry. Wait, for the last question. So this is V of t. And they're asking me, what is the volume of the balloon after 1 minute? So V of 1, that's going to equal 3 times 3 to the power of 3. 3 to the power of 3 is 27. 27 times 3 is 81. If for real? Yeah. The answer is 81. Let's move on. A balloon. Oh, and in fact, I'm just going to put, that's 1. Now, 2. Perfect. So let's put a circle. A balloon is being filled at a rate of R of, bro, what the heck? R of t liters per second, starting with the volume of 0 liters at a time t equals 0. What is an expression that represents the volume of the balloon after 2 minutes in liters? So I really hope it's not as simple as it seems. Let's see. So it does not give me the equation. So it's probably, I mean, it has to be relating to question 1. Yeah, so in my guess, I think I'd just do V of 2 equals 3 times 1 plus 2 times 2, or quantity raised to the third power. This equals 3 times 5 to the power of 3. 5 to the power of 3 is 25, 125, 125, 375. volume of the balloon after 2 minutes. All right, let's move on. The temperature of a city, T hours after 9 a.m., is modeled in degrees Fahrenheit by the function big T of time equals 80 plus 19 sine of pi t, little t over 12. So the temperature of a city T hours after 9 a.m. So this is after 9 a.m. Therefore, we're saying that T of 0 is going to be 9 a.m. But like, anyways, in degrees Fahrenheit equals that. Okay. According to the model, what is the temperature at 9 a.m.? So this is going to be big T of 0. Wait, so let me, for A, in fact, let's make this a little clearer. For A, big T of 0 is going to be 80 plus 19 sine of 0, which equals 80. For B, what is the temperature at 3 p.m.? 10, 11, 12, 1, 2, 3, 4, oops, 10, 10, 11, 12, 1, 2, 3. That's T equals 6. So we have 6 pi over 12. That's going to be pi over 2. Sine of pi over 2, that's going to be 1. 80 plus 19, which equals a 99. Very good. C. According to the model, what is the average temperature over time, over the time period from 9 a.m. to 9 p.m.? Perfect. So using the average formula, 1 over b minus a times the integral from a to b, whoops, of f of x dx. I believe that's right. This implies that we are being asked, hold on, what is the average temperature over time from 9 a.m. to 9 p.m.? Hold on. So the function big T of little t is what is that? It's simply like the position, right? So integrating it won't do anything good. According to the model, what is the average temperature over time? Yeah, so I think this formula for integration is kind of useless because we don't have any integration. We're not derivating anything. So the only thing, like the average, let's see. Hold on. I might be onto something though. 9, it's mod. I mean, I have a feeling that I should do 1 over 12 minus 0 times the integral from 0 to 12 of big T of little t dt. I have a feeling they want me to do that. But the reason I'm conflicted is because this big T of little t is not a derivative. Okay, well, I mean, could that be like an integral, but like the integral of what? Oh, well, of t prime of t. Oh, okay, well, I guess, yeah, right. So I get 1 over 12 minus 0 times the integral from, oops, from 0 to 12 of t prime of little t dt, right? So we get 1/12 times the integral from 0 to 12 of, and then we simply write the derivative of t of big T of little t, and we get 19 cosine of pi pi t over 12 times the derivative of pi t over 12. And that's simply going to be pi t, right? I feel like I'm missing something, but it's okay. Oh, let's keep going. We get, so solving this, yeah, I can't simplify that anymore. So what I will do, integral from 0 to 12. All right, so first, what is the antiderivative? Antiderivative of the integrand is going to be, let's see, it's going to be, oh, okay, well, looks like we're going to have to do U substitution, right, because this is a U substitution problem. Hold on, did I have to do U substitution here? The temperature of a city, T hours after 9 a.m. Is modeled. The temperature, right. Yeah, no, I don't have to. Okay, so C is where they want me to do the integral. So doing the integral, so U equals pi t over 12. Yeah, integration by parts wouldn't work. Trigonomic substitution, yeah, I don't know if that'll work either. So therefore du is going to be, oh, perfect. Yo, okay, I see what they want me to do. What a beautiful substitution right here. Let's go. That's so cool. That's so cool. Well, what do we get? Oh, by the way, and this is dt. So we get 19 cosine of u du. How beautiful. That's just lovely. And the antiderivative of this is going to be 19 sine of u. And then, of course, since it's definite, it's going to be from 0 to 12. And then u is pi t over 12. Perfect. So then, simplifying more, we get 12 over 12 is 1. We only get pi. And then 0, well, that's just 0. Sine of pi, how much is that? Sine of pi, that's 0 as well. Wait, oh no, don't give me another 0, please. For real? Hold on, sine of pi, that's 0. So times 0, the answer is 0. Now, does that make intuitive sense? The average temperature over time from 9 a.m. to 9 p.m. is 0. That does not seem right. Let's see. What did? Oh, I'm sorry. No, yeah, no. 9 a.m. That's t equals 0. 9 p.m. Oh, whoops. We forgot to modify our bounds. Hopefully that's it. So we get, so when x is 0, pi t over 12 is 0. So we get 0 in the lower bound. And when when t is 0. And then when t is 12, we get pi. But there you go. So so we don't have to replace them. You don't have to. Whoops. Beautiful. And sine of pi. How much is, oh, well, that's the same thing. We get 0. Well, that's not cool. What does that mean? Why? Why is that 0? Bro. Uh, hold on. Average, it's not mean value theorem. Hold on, I think I had it in my calc book. Where was it? There it is. No, I mean, we were correct. Yeah. Let's see. Traction 2 viewers. Let's go. Let's go, bro. Anyways, where are we? So, I'm not sure why this turned out to be the way it was, but I think we need to continue. And who knows? Maybe they didn't want like a physically intuitive answer. Okay. So, evaluate the indefinite integral of e to the x over 6e to the x plus 2. Let's see. Let's think, because it looks like something is clear, but I don't know what it is. So first, let's think. Yield substitution. I mean, it's the topic of this review, but I mean, I want to understand why that's the best choice. Would integration by parts work? No, I don't think so. Yeah, but probably not. I don't know. It just doesn't feel right. And based on everything I've done, I think I gotta trust my feelings at some time. Uh, hey, I'm still facts over feelings though. Anyways, let's see. Trigonometric substitution. I don't think so. We have e to the x. All right. Yep. U substitution it is. U equals, well, e to the x, right? Yep. Yes. And du is going to equal e to the x dx. All right. Therefore this will equal the integral of u over 6u plus 2. And anyways, that's not u. That's going to be 1 du. So we've now a fraction. 1 over 6u plus 2. Well, that's easy to calculate, right? Let's see. This is supposed to be really easy. I don't know what's going on. Let's see. Let's see. Over. Let's see. Hold on. I've never been good at the fractions of this part. Mm, so this is no. It's not. Okay. Mm, let's see. 1/6 u plus 2. I mean, it seems really obvious. Oh, yes. Bro, here. I can't get stuck in this for too long. So I'm just going to pull up a chat GPT. We don't have to do any youth up there, right? Hmm. So maybe we use oh, for real? Oh, dude, that sucks. We did it the wrong U. All right, well, again, it's like a trial and error. There isn't a correct way to do it. I mean, I think I could have done 2 U substitutions, but it's okay. Equals 6 e to the x. Gotcha. So we get no, dx. Right, right. Du. Perfect. So then we get ln. Right. So then we get ln of 6 e to the x plus 2. There we go. And that's what he got. Oh, and then of course plus c. Wait, 1/6. Hold on. And why is that? Of course. So okay. All right. I feel like I'm going a little slow. I got to keep going. Okay, so So this looks like integration by parts, but okay, what would be the best u? So if I let u be, let's say 6x plus 3, then du would be 6. Yeah, no, I don't think that would work well. If we let u be x squared plus x, then du would be 2x plus 1. Oh, there you go. Okay. So so we get, but also 2x plus 1, that is probably going to be 3u. Oh, I'm sorry. We think. So if we have du, well, 3, right? A 3 over here. Because 3 times 6x, or 3 times dx plus 1 is 6x plus 3. Perfect. So then we get cosine of u. There we go. Perfect. And replacing back, we get. All right. And I'm going to leave it at that. Hold on. And 3 times sine of x squared plus x. I don't think I can do anything there. Right. A bacteria colony. Hold on. I'm just going to write 6 over here. A bacteria colony. Oh, wait. And is there more? Okay. Wait. Oh, yeah. There's more. All right. Cool. Only starts. Wait. A bacteria colony starts with 200 bacteria and grows at a rate of R of t equals 450, 0.268 times e to the power of 2.25, and so on. Bacteria per hour. Per hour. Gotcha. How many bacteria will there be after half an hour? So like t over 2? Okay, let's go on. So we have okay. Per hour. So I think it's 1 over 2, right? Or 1 over 2. And I believe I need Desmos. The 1/2 is going to be that number. And round to where? Nearest whole number. 1,388. Okay. Well, that's actually really cool. Anyways, let's see, we should let you be. Right. Right in plain sight. Right there. So easy. There we go. Oops, hold on. Yes, right. So. I believe that's our answer. Very good. Volume. Gotcha. Okay. Oh, how about 1/5? Hmm. That's a tough one. Hmm. Oh, how about 2/5? You only get 2/5, right? So that's okay. Right. So if you let. Hmm. Here. Mhm. Cosine of pi, that's got to be 1. Right, I believe that's her answer. Oh boy. Oh, okay, cool. Are you doing statistics? Statistics is calculus, right? Yeah. I bet it's also pretty tough with probabi- probability distribution. There you go. Yeah. Yeah, dude. Oh, hold on. I think I'm gonna take a break, bro. Okay. Well, let's keep going. Perfect. So we have evaluate the integral secant squared x tangent to the power of 4x dx. So this does not look too bad. Oh, think. The derivative of tangent is secant. The derivative of secant is secant tangent. We could do this two ways. We could do u equals tangent, and then du would be secant squared dx. And that could work, right? You had to get u to the power 4. Or we could do u equals secant x, and du would be, okay, I think the first one works the best. So by doing that, we get u to the power 4 dx. Beautiful. Over 5, and tangent of x to the power 5 over 5. That's our answer right there. Let's see, think. Okay, a model for the basal metabolism rate in kilocalories, in kilopascals or kilocalories an hour of a young person is R of t equals 85 minus 0.17 cosine of pi t over 12, where t is the time in hours measured from 5 a.m. From 5 a.m. Gotcha. What is the total basal? Okay, so R of t. All right. Yeah, oh, okay. So it's a rate. Rate. Right. It's right. That is a rate. The rate is right. What is the total basal metabolism of this person for a 24-hour period? So it means, and yeah, t is time in hours. So the integral of big R of t is the integral of 85 minus 0.17 cosine of pi t over 12. U equals, very easy, we shouldn't complicate this. What happens if we let it pi t over 12? Well, we get pi over 12. I don't think that works. If you let, what derivative do we see here? Yeah, I don't think we see anything. To be honest, I feel like I can just take the integral without doing anything. Oh, well, what if I do 1 over 12? No. T over 12, I get 1 over 12. It doesn't work. Power pi t. No, dude. So I don't think we need u substitution here. We just get negative 0.17 sine of pi t over 12, and then times pi over 12. So times 12 over pi. That's just the integral. And then in a 24-hour period, we get, this is going to be sine of, so 2 pi times 12 over pi. And this is equal to, and sine of 2 pi is 0. So we get 0 again. What's this about? Boy. All right, let's finish these 2 questions. And then let's see if we are correct. I'm doubtful that I got all of them correct. I feel like I got many of them incorrect, but I think this was very good. This review served its purpose very well. 12. Let's see. So, well, u should obviously be let's a square root of x, the derivative of that. I don't know if that'll be good. If we let u be sine of square root of x, we'd get cosine O. If we let u be, here, let's do u here. There you go. To square root of x dx. Right. Oh, perfect. So we get, so if we multiply by 2, we get 2 du. Very good. And is it 2? Yeah, it's 2. Perfect. And final question. And then over x dx. So u, I believe it should be ln of x. Yep. Already can see it. Easy peasy. Easy. Okay, we finished. Now let's check if we were correct. And the first one does not look correct. Because we got 81. 3 to the power of 3. 3 squared is 9, 27. All right. They got 5.3 million liters. And where in the world would they get that? Wait, are these other questions? No, these are answers. All right. I immediately see where we got this wrong. t was seconds, but they ask after 6. So not v of 1, they ask v of 60. Cancel v of 60. This is 3 times 1 plus 2 times 60 to the power of 3. 3 times 121 to the power of 3. 121 to the power of 3. Yup, that's exactly what they... Very beautiful. Very beautiful. Okay, let's keep going. So, one, check. I mean, we didn't get it right on the first try, but it's the thought that counts. And we were super close. Question 2. We got 375, and they got the integral from 0 to 120. Where in the frick did they get that? So they said 2 minutes. So we immediately are already wrong. Wait, but why did they respond with an integral? R of t. So this is a... All right. So we have... that represents the volume. So R of t is a rate. So we'll have the integral because we want the volume. You know, we need to integrate the rate. And this is going to be after 2 minutes. So from 0 to 120 seconds of R of t dt. All right, let's keep going. If we would have read that carefully, we would have gotten that right. Question 3. We got t of 0 equals 80. We got the correct. For B, we got 99. They also got 99. Let's go. And for C, we got 0. And they didn't. Oh, because I forgot the 80, did I? The average volume, 80, right. One-twelfth, right, times the integral from 0 to 12, we had that, of the derivative. That's, oh, they did not integrate. Sorry, they did not derivate that. Interesting. All right, let's keep going. I got 1/6 times ln of 6 to the power of e. Whoops. No. There you go. 6 e to the power of x plus 2. And they got the, oh, whoops, in the plus, yeah, plus c. Perfect. That's super correct. Number 5, we got 3 times sine of x squared plus x. We got the same thing. Well, we forgot the c, but essentially correct. 6, we got 388. They got 616. And why is that? Oh, okay, I think I understand why. I know why. After half an hour. Oh, wait, no, but that's per hour. It's not per minute. Okay, it's fine. So we'll put an X on that one, and we'll put an X on this one. We'll put an X on the ones that we don't understand what we got wrong. 7, I got negative cosine of x squared plus 7x. They did too. Well, the plus c, correct. For 8, I got sine to the power 4 of x over 4. They got 1/4 sine to the power 4 of x plus c. I keep forgetting, but essentially correct. 9, I got negative 25 over 2t. That's completely wrong. We will check that later. 10, I got tangent to the power 5 of x over 5. Missed the plus c, but essentially correct. 11, I got 0. They didn't. That's wrong. 12, negative 2 cosine of square root of x. Yep, I got that. Forgot the plus c. Essentially correct. 13. Negative cosine of ln of x plus c. Correct. All right. What? What's this? The same thing. Anyways, well, that went actually much better than I thought it would. But I believe it is time for dinner. So that's why we are going to stop now. And we will resume our studies tomorrow. Well, everyone, it was a blast. It was a blast doing this. We will, in fact, do this, but tomorrow with speed and agility. And yeah, not much else to say. Thank you all, everyone, for coming. It was a bunch of fun, and I will see you all next time. Thank you.